Welcome. In this video, I will prove the linearity of the expected value of a random variable, and I will state and prove two formulas for the variance, one general formula and one formula that specifically applies under a linear transformation. All right. So the first formula is that, let's say we have a nice little random variable that is a linear transformation of another, where you multiply by some number and you add some constants. This could be the calculating from Celsius to Fahrenheit, or the other way around, or any linear combination of changing variables. Then our formulas state that the expected value of y will be a times the expected value of x plus b. Which in essence just says that the expected value is a linear operator. All right. The second formula is that the variance for any random variable can be calculated as the expected value of the random variable squared minus the expected value squared. Nice little result there. And then the last result that we use this result is that specifically for the variance of y, it will be a squared of the variance of x. Beautiful. All right. Let's check out the proof. Okay? So we have the definition of the expected value. The definition of the expected value of y is, well, it's the sum of all the random values multiplied by the respective probabilities. Okay? But, well, we have that the definition of y is that it's ax plus b. All right? Let's isolate x here. So we get the probability that x is equal to, well, it's going to be subtract b on both sides, so y minus b, and then we divide by a. Now, hopefully that's not a huge stretch for you to believe that that's how you isolate x here. If you don't see that immediately, you can just pause the video and check it out. All right? Well, then I make a little change of variables here. Well, I change y out for something else, namely ax plus b. All right? Because this variable here will have the nice little beautiful effect that will be exactly the same as this fraction here. If x is equal to this fraction, then y will be equal to this expression. Now, again, hopefully not a huge stretch. All right? Now I can use the linearity of the sum to make our little conclusion here, which is that this will become a times the sum of x times the probability that x is equal to x plus b times the sum of the probabilities. Well, this is equal to a times this. What this is exactly the expected value of x. That's what this is the definition of the expected value of x. Well, what happens to the second sum here? Well, this is the probability of all the probabilities of x. But as I often say, something has to happen. So this will be 1. So that's why we end up with this beautiful result. All right? If you want to check out any of these arguments, you can roll the tape back or pause here and check it, look through it, right? Because I'm going to continue to the variance now, all right? So the variance of x, any random variable x, is going to be the expected value of x minus mu, where mu is its expected value squared. Because that is kind of the definition of the variance. You take the x minus you take the average squared distance from the mean. That is exactly what the variance is. Well, we can just use what we just proved, well, the linearity of the expected value, and use we used the squares of this difference to get x squared minus 2 times mu times x plus mu squared. Right? The linearity says I can split these up into these three terms. So we get the expected value of x squared. We get minus 2 times mu. Well, mu is simply the expected value of x, as I already said. And then I get the expected value of x here, plus the expected value of x squared. But the expected value of x multiplied by itself is just the expected value of x squared, just like this term. But I have two of these and just one of these, which means the expected value, we get expected value of x squared minus just one of these. Is that nice? Is that a nicer way to calculate the variance? You don't have to do all kinds of fancy sums and stuff. Alright? So let's check the last one out, alright? Let's do the variance of y. Well, it's the expected value of y squared minus the expected value of y squared. I mean, I know it sounds weird, but hopefully from when I'm writing the context, the meaning is clear. All right, and then we again use that this is the expected value of ax plus b squared minus the expected value of this squared. But the expected value of y we already showed is this. That is actually a times the expected value of x plus b squared. Alright? So let's take the first one here. We get the expected value of a squared x squared. Again, we're taking the square of a sum, so that gets we can expand that into this. We get plus 2 times a times x, 2 times a times b times x plus b squared. And then minus a squared, the expected value of x squared, minus 2 times ab, expected value of x, minus b squared. So this thing is from here, and these three terms are from here. All right, well now we can use the linearity, and we get the expected value, we get a squared times the expected value of x squared plus 2ab, expected value of x plus b squared. And then minus a squared, expected value of x squared, shoot, this would be here, sorry, squared, minus 2ab, expected value of x, minus b squared. But now, wonderfully, this will cancel with this. This will cancel with this. And all we have left are these two terms which coincidentally have a common factor of a squared. And what's left from the first one? Well, we have the expected value of x squared, and then minus the expected value of x squared, which is a squared times the variance of x. Beautiful. So just because you change data sets, you change your random variable in some kind of linear manner, does not mean you have to redo your whole analysis. All you do is you find take your expected value that you maybe already did, you take the variance that you already did, and you just make the linear transformation of the expected value, and you multiply the variance by this gradient factor here, square. And the wonderful part about this is that because the standard deviation is actually the square root of the variance, this means that the standard deviation will actually just be multiplied by a. And that is one of the beauties about using that definition of the standard deviation. Even though it's not specifically the average of the distances, it makes it so that a lot of these calculations, these transformations, are so nice. So that's one of the big motivations behind calculating the standard deviation in the way that we do. Beautiful. If you have any questions or comments, feel free to leave them below. All right.